Well, in homework 2.3a, we're going to take a little bit different twist. Everything up to 2.2d assumed that our matrix was fully populated with usable numbers. Yeah, it might have some zeros here and there, but there was no reason not to think that every position in the A matrix had a non-zero value. In reality, most applications that are large applications have structured zeros scattered throughout. Very true on our finite element analysis that we use for designing airplane structure. Can we take advantage of patterns of zeros that we know in advance will be there? Okay, so your homework is to load matrix A and vector B from this time a3.xl. Now that file has a 10 by 10 tridiagonal matrix of the kind that we discussed in the lecture. Your job then is to triangularize the matrix A in place. Make sure that the algorithm that is used is order of n rather than order of n cubed. You're going to carry the augmented vector B in place just like we did before. So we solve the solution. And on our back substitution, we're going to make sure that it is also order of n. Now the way you're going to do that is going to be to use homework 2.1 as a base. Homework 2.1 is clearly order of n cubed on its diagonalization, and its back substitution is order of n squared. So we'll need to improve that. Okay, after you're done improving that, then you're going to compute and print our normal matrices and vectors of interest, the A matrix, the B vector, and also our solution vector x, as well as the rank. And you'll print that out in your submissions. Okay, so let's talk about how we're going to go about doing that. As I mentioned before, go back to homework 2.1. In practice, you wouldn't do this because you shouldn't use naive row reduction in any commercial code. But just to make this more straightforward and simple, we're going back to our simplest code, which is 2.1. So change your input file using a3.xl. You're going to take a look at every calculation that's in our logic, in the 2.1 logic. So take a look to see if the row index and the column index will differ by more than 1. If that's the case, you're not on the main diagonal, the super diagonal, or the subdiagonal. That means the value must be 0. Okay, now with that information, go to your script and limit the range of the for loops, because the for loops are going to go across all the rows and all the columns regardless of the relationship of I and j. But see if you can't improve the efficiency by limiting the scope of the for loops anytime the difference of I and j in absolute value exceed 1. Now when you do that, you'll find that 2 of the 3 loops that are there, the inner loops, don't need to be loops at all because they are very limited to the number of occurrences that are going to occur. So if you find that you really don't need loops and you could get away with just maybe 1 or 2 calculations, then do that and get the loop out altogether. That's going to guarantee that you have an order of n calculation. So you need to do that on the diagonalization portion, and you also need to do that on the back substitution. Okay, so also take a look if any calculation that you have there necessarily will produce a 0. If that's the case, just assign it to 0 because it's cheaper to set something to 0 than calculate it to be 0. And that will give you a very efficient set of code. You better test it to make sure you get the same results as if you use 2.1 directly. And then when we're done, I'll send you out a solution PDF. So this will, again, not have a solution video. I will just send you the solution PDF for that. So there you go. Give it a shot. We'll see you next time.